In this lesson, we're going to take a look at solving rational equations and inequalities. And the fantastic news about that is that we already actually have pretty much all the skills we need to do this now. We just need to try a few of them and see how they actually work. There is a little bit of a trick to inequalities that we're going to have to play with, and well, we'll see it when we get there. On that note, let's get there. So for the first one, we just want to solve for x algebraically. These could also be solved for using Desmos or Mathway or a whole number of other options. But to solve these algebraically, well, let's see how they work. So the first one we have, a, is just 4 over 3x minus 5 equals 4. So what I'm going to do is I'm going to, first of all, make a little note here is that we want to be able to state any restrictions, and specifically that would cause a vertical asymptote. Um, Basically, anytime the bottom of a fraction is equal to 0, we have a problem. So I'm going to make a little note, or I'm going to put up a little pen mark here that we want to state the restrictions. And I'll come back and do that once we've actually solved. The first one, I'm sure you could actually solve right now without my assistance whatsoever because it's actually pretty straightforward. You just have a fraction equal to 4. What I'm going to do then is multiply both sides by 3x minus 5, and that's going to be 4 equals 4 times 3x minus 5. Now, I did skip a little step where on the left I didn't write 4 divided by 3x minus 5 times 3x minus 5. I just mentally canceled those out. At this point, I can divide both sides by 4, or I could expand on the right-hand side, whichever you wish, but I think it's easier to divide both sides by 4 right now. I'll add 5 to both sides. And finally, I'll divide both sides by 3. By the way, when I did the division by 3, I also just flipped the sides so that I'm writing the x on the left, but I don't have to do that. Okay, so my answer then is x equals 2, but there is a restriction. The restriction is that 3x minus 5 cannot equal 0, which means that 3x cannot equal 5, which means x cannot equal 5/3. So here's the question. Is that even an actual restriction? Well, our math says that x is equal to 2, but it can't be equal to 3 over or 5 over 3. Well, it actually can't be equal to anything other than 2. So this one, who cares? It doesn't actually matter. This restriction doesn't do anything because we're actually looking for an answer for x, and saying one of the many things x isn't is irrelevant. Now, if for some weird reason the restriction became x is not equal to 2, then there'd be no solution to this problem. Even though our math on the left said x is equal to 2, if our restriction says it isn't, then it isn't. But in this case, it really doesn't matter. Yes. Well, let's try another one. Now again, you've got the algebraic skills to be able to solve something like that, or at least to get it started. I will tell you, however, that your instinct to multiply or cross multiply and expand both sides is not wrong, but it's going to lead you into a buttload of hurt. Looking at those are not pretty equations to try and solve if you cross multiply. You're going to get a large polynomial on the left and an even larger polynomial on the right. So here's my advice. Always try to factor first. If we do that, on the left-hand side, we get x minus 5 on the top, and on the bottom, we have a simple trinomial, and we need two numbers that multiply to -4, add to -3, and I think that's going to be -4 and +1. So x minus 4, x plus 1. And yeah, that'll give me the -3x and the -4. On the other side, I'm going to have 3x plus 2, which doesn't factor. It's about as simple as it can get. But on the bottom, I have a difference of squares. So I can factor that down into x minus 1, x plus 1. Okay, well, here's a little advantage. If we have an x plus 1 on both sides, we can multiply both sides of the equation by x plus 1, and those cancel. However, that gives me the restriction x cannot equal negative 1. I'm just going to write that over to the side for now so I don't forget about it. Now that I've done that, I don't see anything else that cancels out, unfortunately. But it is going to take uh, nasty polynomials and make them manageable polynomials by multiplying by a little less. So now I'm going to cross multiply, multiply both sides by x minus 1 and x minus 4. Oh, I'm going to make a little note here too. Even though we haven't canceled them out yet, if x is, oops, let me try a different color here. If x is 4 or x is 1, we're also going to have division by 0. So I'm going to add those to my list of things x can't be. It can't be 4, and it can't be 1. We'll see if any of these matter. So they may not. If they don't have solutions of those, then it doesn't change anything. Okay, so that gives me x minus 5, x minus 1 equals 3x plus 2, x minus 4. I wish two of those were the same, one on each side, but they're not. So the best we can do at this point is to expand. That gives us x squared minus 6x plus 5 equals 3x squared. We got plus 3x minus, 3x squared plus 2x minus 12x is minus 10x minus 8. Not the prettiest, but I'm going to move everything to one side. I'll choose to move it over to the right. And so when I move it over, I'm subtracting an x squared from both sides. I'm adding 6x to both sides. And I'm subtracting 5 from both sides. Okay. At this point, we've got to solve that. We can solve it using a whole number of methods that we saw back in Unit 1, or maybe Unit 2, definitely before this. We could try factoring it. If that doesn't work, we'd use a quadratic formula. And if I try to factor that, two numbers that multiply to negative 26 add to negative 4, I'm not seeing it, to be honest. So I'm going to use a quadratic formula and say x is equal to, remember that's a, b, and c. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And now inside that bracket, negative 4 squared is 16. Negative 4 times 2 times negative 13. That all works out to be root 120. And now my suspicion I know is correct. That's not something that's a whole number, so we would never have been able to factor it. What I can do though is say that 120, was that divisible by anything, any perfect squares? It's divisible by 4. At this point, I'm not sure if it really matters if we need to make it that much nicer, but I could say it's 4 plus or minus root 4 root 30 over 4, which is 2 plus or minus square root of 4 is 2 divided by 2 root 30 over 4. Okay. From there, I could leave them like that, but in most applications, we kind of want to have some idea what those numbers actually are. So I'm going to do 2 minus the square root of 30 over 4. It's negative 0.869. And I'm going to do 2 plus root 30 divided by 4, which is 1.869. So two numbers we never would have got by trying to factor the trinomial, but it works. So these are our solutions, and we do have a couple of restrictions there, but do the restrictions matter? And in this case, they do not matter. We've eliminated negative 1, 1, and 4, but those are not the solutions anyway, so it doesn't really affect anything. Okay, I've kind of buttered up against my next question, so I'm going to cheat like I usually do and slide that out of the way. Oops. Oh, come on. Be nice. Not sure why it keeps disappearing on me. Okay, it's not very out of the way, but it's enough out of the way. Next one. X squared minus 2x minus 8 over x minus 4 equals 6. Same thing. Let's start by factoring to make sure that we can't cancel anything out. We need two numbers that multiply to negative 8 and add to negative 2. And I think those numbers are negative 4 and positive 2. Oh, and I already see an advantage here. And that's that I can cancel out the x minus 4s. But I'm going to make a little note over here that x cannot equal 4. Maybe that'll come up, maybe it won't. Once we've done that, I have x plus 2 equals 6, x equals 4. So there's my solution, except x cannot equal 4. And that means that this has no solution. And sometimes that happens. It's kind of weird. It's kind of coincidental, and it's kind of not a coincidence that I made one that worked like this. But we have one where the only mathematical answer doesn't actually work because it results in basically an invalid answer because it required us to do a division by 0. Okay, so no solution on that one. Let's solve for x using technology and check with a left side, right side proof. We're going to do that because, well, frankly, those are nasty looking little things, and we don't want to have to always deal with them. But that's okay. Desmos to the rescue. Oh, and I got some stuff in here already from the last lesson. Let's get rid of that. Okay, so we have x over x minus 2 equals 2x squared minus 3x plus 5 over x squared plus 6. Well, that's a mouthful. So what I'm going to do is I'm going to let the left side equal a function. So the left side is x over x minus 2. And I'm going to let the right side be its another function. And the top we have 2x squared minus 3x plus 5. And the bottom we have x squared plus 6. Okay, so there's our two functions. And then the question is really, when are they equal? It looks like they're never going to be equal on the left-hand side. I think I only see one value where they look like they're crossing each other. And that looks like it's right about there. So I'm just going to make a little note on our page. Desmos says the answer is x equals 6.466, at least rounded. I don't know if that's supposed to be a fraction or something. It could be, but I think it's just a number. So those two look like they're equal there. Okay. Going to go back now to my page. And before I go too much further, I'm going to point out that there are a couple of restrictions here. From the left-hand side right there, x cannot equal 2. And on the right-hand side, the bottom, there actually is no restriction because x squared plus 6 will never be 0. It's always going to be 6 or greater. So now a left side, right side proof. I'm going to remind people that a left side, right side proof actually means dealing with the left sides and right sides separately. You can't just plug it into the equation and say number equals number. So we have to do this. Left side equals x over x minus 2, and then separately, right side equals 2x squared minus 3x plus 5. And one of the reasons we have to do this, besides I told you so and it's good form, is because when you do number equals number, it is quite possible to do illegal operations where you're doing something to both sides instead of treating them separately. And there are lots of times where you can do something to both sides that will make them equal, but was never true in the first place. Just as a little example, and I'll erase it in a moment, but no one here, I believe, thinks that 2 equals 3. But if I say, okay, I'm going to multiply this side by 0 and this side by 0, and that's true, so therefore that must be true. That's something bad that can happen when you're dealing with left side, right side proofs and you're not actually separating them. And that is why we are going to always separate them. Okay. That can go away now because I don't want anyone to see that 2 equals 3. It's not true. All right, so now what we do is we plug in the value that we think is correct and see if it works. And I will point out that there could be a small variation just because we do have a rounded number here. But when I plug that in, 6.466 divided by 4.466, I get out 1.448, roughly. It's actually 7828034, etc. On this side, 2 times 6.466 squared minus 3 times 6.466 plus 5 over 6.466 squared plus 6. I'm just going to do the 6.466 squared. And that's going to give me on the bottom here a 41.809 plus 6. And on the top, 2 times that is 83.618 minus 3 times that, just 19.398 plus 5. And hopefully this works. 83.618 minus 19.398 plus 5 is 69.22. And on the bottom, 40, I can do this one in my head because it's easy, 47.809. And then when I divide them, I get out 1.448. And hey, there we go. Those are the same. So we have shown that that is the correct answer. I guess I didn't need to put the box around Desmos as well, but Desmos gave it to us, so let's at least give them some credit for it. The answer for x in this case is 6.466. That saves us a lot of time over doing it algebraically, even if we did do a left side, right side proof algebraically. If you haven't tried so already, maybe it's a good time to pause and do this on your own. But regardless of whether or not you pause, I'm going to go ahead and do it. And I'm going to go over to Desmos to do that now. So the first fraction we have on top is x squared minus x minus 6. Oops, I want that to be on top, not at the side. And on the bottom, I have x minus 3. For my right side, I have an x cubed plus 3x squared minus 8x minus 10. And on the bottom, I have an x plus 1. Okay, I'm going to flip back for just one moment because I want to remind myself. There are a couple restrictions on this one. Anything that makes the bottom 0. So x cannot be 3 and x cannot be negative 1. Just never want to forget those restriction checks. Okay, so it looks like they intercept at 2 points, -4, -2, and 3, 5. So that means that my solutions, according to Desmos, are going to be -4 and +3. So I'm just going to write those down. -4 and +3. And now let's do a quick left side, right side proof. And I'm just going to put that here for x equals -4. Left side equals -4 squared minus -4 minus 6 over -4 minus 3. Now, thankfully, these are whole numbers, so this is a little bit faster. We have 16 plus 4 is 20, minus 6 is 14 over positive 12, which is 7/6 if you want to put it as a fraction in those terms. And then the right side is equal to -4 cubed plus 3 times -4 squared minus 8 times -4 minus 10 over x plus 1. Okay, -4 cubed is going to be -64. Plus 3 times 16 is plus 48. -8 times -4 is plus 32. Minus 10 is 6. And on the bottom, we have -4 plus 1 is -3. Interesting. So that gives us -2. Those are not equal. Wonder why that is. Whenever I get something that doesn't work out the way I'm expecting it to, it's always a good idea, especially since this is a check. The whole idea of a check is to see if I did something right. I'm pretty sure I did because it was Desmos. I had to go back and just check to see if I made a mistake, and I already see what that mistake is. Thankfully, I'm usually half decent at catching these. That should be -4 minus 3, not -4 times -3. So let me fix that. Okay. And when I fix that up a little bit, I get 14 still on the top. I get -7 on the bottom, and there we go, -2. I'll be honest with you, when I do this, sometimes I'm wondering, do I go back and edit out my mistakes? Ooh, I'm going to edit out the fact I just used crayon. Do I edit out my mistakes, or do I own it, point out that I'm a human being too, and learn from them? So I was suspicious, went back and checked my work, and sure enough, I found the error and was able to correct it relatively easily. So our left side and our right side are equal. Not sure why I'm bothering to write QED, but I felt like it. And now I should go back and double check the same thing with x equals 3. except, I know that x cannot equal -3 because that's one of my restrictions. So now the nice thing is I don't have to do a left side, right side proof for that one. And if I did, it would immediately give me a 0 there. So I'd be wasting my time. So it turns out that the only answer I get, regardless of what Desmos says, is -4. That's the only answer to my question. Now, I think I will go back and show you why Desmos gave it, and this will come out actually in the next lesson a little more, but let's foreshadow, shall we? Those are the two intersection points at 3, 5, and -4, -2. I'm going to turn off the purple graph for a second, though. And I want to show you what happens at x equals 3. So there's x equals 2 in a bit. Turns out it's actually undefined at x equals 3, just at that one point, which makes sense because it makes the bottom of the fraction 0. And that's something that we're going to look at in the next lesson. It's called a discontinuity, specifically a removable or hole discontinuity. A hole as in H-O-L-E because it's literally a hole in the graph. Replaceable because somebody thought that was a good idea to call it. But that looks like a straight line. It's actually a straight line missing a point. And because of that, there's no actual intersection there, despite the fact that it looks like there is. So even Desmos can make mistakes if we're not paying attention. This is why we have to understand how the math works from a fundamental level. All right. Let's keep going. We've got an inequality here to solve. The math looks easy. The numbers are small. We have 2 over x minus 5 is less than 10. I'm going to put a little note here, and under no circumstances is x ever going to equal 5. It's not allowed. It's definitely a restriction. Okay, so let's subtract 10 from both sides and see what happens. If I subtract 10 from both sides, I get 2 over x minus 5 minus 10 is less than 0. Well, I've got two terms on the left. The only way I put them together is if they're fractions. So 2 over x minus 5 minus 10, making a mess here, 10x minus 5 over x minus 5. That gives me 2 minus 10x plus 50, still making a mess, over x minus 5 is less than 0. Okay, and we can do a little bit there. We can kind of put some like terms together. And we're going to get negative 10x plus 52 over x minus 5 is less than 0. That doesn't look nice to try and solve at all. So what we can do, however, is pretend for a second. Pretend. I'm going to pretend that we're just talking about it's equal instead of less than or equal to. So negative 10x plus 52 over x minus 5 equals 0. We can multiply both sides by x minus 5, provided x is not equal to 5. And that gives us negative 10x plus 52 equals 0. I can then move the 52 to the other side. Equals negative 52. And I can multiply both sides by negative 10, or sorry, divide both sides by negative 10. And that's going to give me 5.2. Okay, so x is 5.2. Any number less than 5.2 should work. Again, going back up here to a different color. If x equaling 5.2 makes that equal to 0, anything, oh wait, this is minus. We got to be careful here. Anything greater than 5.2 should make that whole thing less than 0. And if you're not sure about that, actually, let's try it this way. I'm going to do a little mini graph once I get my pen to work. And I'm going to say 5.2, x equals 5.2. And you know what? Just for the heck of it, I'm also going to put on x equals 5 just in case it becomes a problem. And I'm going to do a test on each of these regions. There's actually 3 regions here. We got less than 5, between 5 and 5.2, and greater than 5.2. I'm going to test a point and see if it makes the inequality true. Okay, so if I test a number bigger than 5.2, I'm going to choose, I don't know, I think 1,000,000. And if I plug 1,000,000 in for x in my equation, again, up here, if I plug in 1,000,000, I'm going to get essentially negative 10 million over 1,000,000, which is negative 10. Either way, it's a negative number, so it will be true. It will be less than 0. What if I plug in, if you, by the way, if you don't believe me, you can pick any number you want, like pick 10 and plug it in. In fact, why don't we pick 10? If you pick 10, you're going to get negative 100 plus 52. And on the bottom, you get 10 minus 5, which is 5. So you get negative 9.6. Either way, negative something means it's less than 0. So that's going to work. Now, unfortunately, we got a really small middle region there between 5 and 5.2, but it is a region. So let's choose 5.1. So negative 10 times 5.1 plus 52 is a positive number. And the bottom is a number bigger than 5 minus 5, so it's also a positive number. Positive over a positive is positive. It is not going to be less than 0. So that region doesn't work. And then the easiest number I can pick for the region below 5 is 0. That just gives me 52 over negative 5, which is positive. Or sorry, 52 over negative 5 is negative. So that's going to make it less than 0. That's true. And so our conclusion is that x is greater than 5.2 or x is less than 5. And before I go any further, I really am going to go over to Desmos and just make sure that that is correct, because it kind of freaks me out. So going over here, I'm going to plug in the original function, which was y equals 2 over x minus 5. And that gives me this graph. And I want to know where it's less than 10. And it looks like it is less than 10 for any x value bigger than 5.2. And it looks like any number, yeah, between 5 and down is also going to be negative. The only place that it's positive, it's bigger than 0, is this little wee region between 5 and 5.2, where it's up above. Everywhere else, the function is below the red line. So I think we did it right. This is the part 5 is greater than, or sorry, x is greater than 5.2, and this is the part where x is less than 5. Hooray, we actually did it correctly. The fact that I'm the teacher and I was skeptical says something. Okay, let's try to do the same question again, but I'm going to multiply both sides by x minus 5. So we have 2 over x minus 5 is less than 0. I'm going to multiply both sides by x minus 5. Oh, sorry, that should be 10, not 0. So that gives me 10 times x minus 5. Now I want to point out that multiplying both sides of the fraction or both sides of an inequality by something leaves the sign the same as long as the sign of that thing is positive, which means that this is only true if x is greater than 5. And if x is less than 5, then that means that a number less than 5 minus 5 is negative. It means I actually have to flip the sign because I'm really dividing or multiplying both sides by a negative number. This, by the way, is hugely confusing. For those who are a little bit lost, I will tell you that this inequality stuff with rational functions is probably one of the hardest things we're doing in the course. So you'll be happy to know that it doesn't get much worse than this. And that's if x is less than 5. Okay, so we have two cases. One if x is greater than 5, one if x is less than 5. So then we go through here and say 2 is less than 10x minus 50. Add 50 to both sides. 52 is less than 10x. 5.2 is less than x. Okay, so that's another way of saying that x is greater than 5.2. Well, that's the result we got up here, so we're doing okay so far. Now for the next one, 2 is less than 10x minus 50. 52 is less than, sorry, is greater than 10x. Did I reverse the sign on this one? Nope, I think we're good. 5.2 is greater than x. And unfortunately, this yields the exact same. Oh, no, it doesn't. Okay, so this is that x is just less than 5.2, but we saw up above that x is less than 5. Here's the trick. X is less than 5.2, but this is making the assumption in the first place that x is less than 5. So we have both those restrictions. It has to be less than 5.2, and it has to be less than 5, which means that it's just x less than 5. So that's our other possible solution. Now, I'll leave it up to you to decide whether you think that is nicer or you think that is nicer. In some ways, B is mathematically a little bit prettier and a little shorter to write out. And it's okay as long as you remember this part. You have to take those restrictions in mind. This just said x is bigger than 5 and x is bigger than 5.2. And the only one that makes both those true is it's bigger than 5.2. Over here, we're told x is less than 5 and it's less than 5.2. Well, it has to be less than 5 then. Alrighty. One other little way we can do it is using technology. Ta-da, we did. So we are done, at least that question. And we get the same answer. X is greater than 5.2 or x is less than 5. Let's try number 4. Okay, this one here looks nastier than the rest. I think we can actually do it easier. So I'm going to show you how I like to do these inequalities. And it's not by multiplying both sides by something or adding something to both sides and all that stuff. I find that really confusing. It's a little bit like we did in the part A above, where we just look at cases. So the first thing I'm going to do is just factor and see if I can make this any prettier and find if there's any restrictions. So on the top, I think that's factorable. Two numbers that multiply to -2 add to -1 are +2 and -1. Sorry, -2 and +1. And on the bottom, two numbers that multiply to -12 add to +1, and that would be +4 -3. Unfortunately, nothing cancels out, but that's okay. I'm going to put a little note over here. I know now that x cannot be -4 or 3. So what do we do from here? Let's take a look at anywhere the graph is a 0 or a 0 on the top or on the bottom. Okay, so I'm going to draw a little number line over here. And I'm going to put on the numbers that give me 0 on the top or the bottom in order, but don't worry about spacing or anything like that. Basically, we're going to be looking for -4, -1, +2, and +3. These are by no means equally spaced or anything like that. They're just numbers on a number line to show us the order things happen in. And so that's going to give us 5 regions we have to check. Below -4, between -4 and -1, between -1 and 2, between 2 and 3, and above 3. So we're going to plug in some points and see what happens. If I plug in a number less than -4, I'm going to choose -5. When I do that, I should get, and I'm just going to pause it while I punch it in my calculator, and I get like 28/8, I think, which is greater than or equal to 0, so that's going to be true. So that makes the inequality true. A number between -4 and -1, I'll choose -2. That gives me a negative on top and a negative on the bottom, negative over negative. Does it give me a negative? No, sorry, it gives me a positive on top and a negative on the bottom, so it's going to be false there. Between -1 and 2, I'll plug in 0. That's going to give me a negative on the top and a negative on the bottom, so it'll be positive when I divide. That's true. It's greater than 0. 2.5 is going to give me a positive times a positive on the top and a positive times a negative on the bottom, so it'll be negative overall. That's false. And then a number bigger than 3, I'll just choose 10. On the top, I have positive, positive. On the bottom, I have positive, positive. Everything's positive. It is greater than 0, so it's true. So I believe the solution to this is x is less than or equal to -4. X is greater than or equal to -1, less than or equal to 2, and x greater than or equal to 3. That actually seemed easier than the others. So we're just looking for places where the top is 0 or the bottom is 0, and then we're testing regions. That's it. What I'm going to do now is just hop over to Desmos and see what it looks like. And I've already punched in the equation. So there we are. And I want to know where this graph is greater than 0. And it looks like here, anything below -2-ish or -4-ish. And then it's above 0 again between here and here. There's my -1 and 2. And then it's above 0 again over here at 3 or bigger. So I think we were correct. So what did we do? I'm just going to remind you, use zeros, top and bottom, and test regions. And if you like, I've seen people that do this, and sometimes I've done it too. I'll remind myself that the -4 is an asymptote, and the 3 is an asymptote, and that those 2 points are zeros. So essentially the graph is doing something I know like this. I don't know the exact shape, but when I go back, yeah, that's pretty much what it does. And then in between, where it's less than 0, it does something like this. That's, oops, sorry. Something like the yellow. That's just a horrible drawing, but you get the idea. Okay. I think I've beaten that dead horse in. And again, this is one of those things that you're going to need to try and do it on your own to understand it. So go do that now, and I will definitely see you with some questions, and if not, in the next lesson.